Hi, welcome to our project, Deep Learning in Space Exploration. Our team leader, Hamish Katyal, and team member Himanshu Sharma have created a hybrid project that mixes machine learning with deep learning to explore the unknown, that is, space. Hundreds of exoplanets have been discovered using nothing but manual functioning of the human eye, but using deep learning to analyze and identify thousands of potential exoplanets at once will ease the human species.
These are some of the roles of deep learning in space exploration. In this project, we will implement these roles to develop a working model of a unique application of deep learning. Although deep learning has a lot of uses and applications in space exploration, for our project, we will be focusing on exoplanet identification using machine learning and deep learning. In this figure, the habitable zone graph shows where planet could have just the right condition for water and life, offering hope for discoveries beyond our world. Deep learning serves as our cosmic compass, guiding humanity through the vast expanse of space, unveiling its enigma and propelling us towards the frontier of celestial discovery.
Let's say you're a budding astronomer looking to find an exoplanet, which are basically planets that orbit stars outside the solar system. Maybe the first instinct of yours would be to just point a telescope into the sky and look around. But it's unlikely you'll find one. Why, you ask? Well, these planets are really far away, but the main reason it's so hard to find them is because the stars they orbit are far too bright and cause a lot of glare. Instead, you often have to use indirect evidence to point to the existence of something out there. Now, there are many existing options for you to choose, and they all work. But out of all of these, one has proved to be the most successful by a huge margin. This is the transit method, an astronomer's superpower for finding exoplanets. Let's see what it is and how it works. Most stars emit light at a roughly constant rate. So, if you measure the intensity of light produced by a star over time, you'd get a straight line. Now, if there's an object orbiting the star, like this exoplanet shown here, and it moves in front of the star, it would block some of the light emitted, and there would be a slight dip in intensity recorded on the graph. Astronomers use this as evidence to point out the existence of a pretty big object, like an exoplanet, in the star system. But this does more than simply indicating that a planet is out there. Here, you can see two different planets orbiting the same star, which I've drawn separately for your understanding. The bigger planet clearly blocks more light than the smaller one, and so the graph records a much deeper dip in intensity. And based on this, you can get clues on the planet's size too. But through the transit method, you can also gauge the time it takes for the planet to orbit the star. Let's look at two consecutive dips in intensity of this graph. Remember, each dip in intensity occurs when the planet comes in front of the star from your field of view. So the time it takes for two dips in intensity is the time it takes for the planet to orbit the star once, which is the planet's orbital period, or as we call it on Earth, length of year. So there you have it. The next time you go out looking for exoplanets, use the trusted and handy transit method. Just don't forget to bring an industry-grade satellite.